All right, today we are diving into the truly weird, almost unbelievable behavior of light when it gets right up close to a black hole.
So, when you think of a black hole, what's the first thing that comes to mind? Probably this, right? A giant cosmic vacuum cleaner. Its gravity is so powerful that once something crosses that point of no return, the event horizon, nothing gets out, not even light. And look, that's a pretty solid picture. It's mostly true, but it's not the whole story. What if I told you that in a very specific zone, outside the event horizon, the rules for how light escapes get flipped completely on their head?
To really get this, we have to talk about a cosmic dividing line. It's a very precise boundary in space where the physics we think we know starts to get, well, really, really strange.
Okay, so physicists have a term for this, effective potential. But let's just make it simple. Think of it like a giant energy hill. For a photon, a little particle of light, to escape the black hole's pull, it needs enough energy to climb up and over the top of this hill.
And this graph from the source material shows that idea perfectly. See on the far left? That's the black hole's event horizon, labeled RS. As you move away from it, to the right, that energy potential shoots up, forming a hill. And that peak right there, that's the highest point light has to get over to have any chance of escaping.
Now that peak isn't just in some random place, oh no. It exists at a very precise, very important distance. The top of that hill is located at exactly 1.5 times the black hole's Schwarzschild radius, and that's the radius of the event horizon itself. This exact distance, 3/2, is our crucial dividing line. It's what separates the world we kind of understand from the world that gets truly bizarre. So, let's start with the normal side of things. What happens to light that's coming in from far away on the outside slope of this energy hill?
Just picture a photon zooming in from way off on the right of that graph. It's heading towards the black hole, towards this big energy hill. What can happen to it?
Well, it all comes down to how much energy it's packing. If it has a ton of energy, it'll just cruise right over the hill and get scattered away no problem. If it has exactly the right amount of energy to just barely reach the peak, it gets stuck in this really delicate, unstable circular orbit. And if it just doesn't have enough juice, well, it can't make the climb and it plunges right into the black hole.
These simple little drawings from the source paper show it all. You've got the scattering, that unstable orbit, and then the final dive in. So far, this all feels pretty intuitive, right? It makes sense.
This is where our whole cosmic vacuum cleaner idea pretty much works. But the really mind-bending stuff starts when a photon begins its journey on the other side of that hill, deep inside the danger zone.
Okay, so let's cross that boundary now. Let's go explore that region between the event horizon and the very peak of our energy hill.
So, what happens if a photon is born right here, inside this boundary, on that steep slope leading right down into the black hole? I mean, common sense tells you there's no way out, right? It's all downhill from there. Looking at our graph again, we're now in that valley between the event horizon and the peak. And from here, that peak looks like a massive wall blocking the path to freedom. But it's a wall that just breaks all the rules you think you know.
And this, right here, is the core paradox. It's wild. If you're in this zone and you aim a beam of light almost towards the black hole, it can actually get slingshotted around by gravity and fly out over the hill. But if you aim it directly away from the black hole, trying to escape, it gets pulled right back in.
Yeah, let that sink in for a second. To escape, you have to aim almost directly at the thing that's trying to trap you. If you aim for what looks like freedom, you're captured. This is just the bizarre, warped reality of space-time this close to a black hole. It's totally backwards.
So what does all this strange, paradoxical physics actually mean? Like, what would this look like in the real world?
Well, the paper gives us this fantastic thought experiment. Imagine you're on a spaceship and you're falling towards a black hole. You've just crossed that critical 3/2 boundary, and you're holding a flashlight trying to send a signal out to the rest of the universe. And the source material puts it perfectly. If I hold a flashlight and move from r equals 3/2 rs to rs, the flashlight will appear dimmer and dimmer to the observer far apart.
And the reason why is that crazy paradox we just talked about. As you get closer and closer to the black hole, the range of angles, the literal cone of light from your flashlight that can actually escape, it gets narrower and narrower and narrower. Eventually, only a beam pointed with impossible precision could ever get out. So from our perspective, light years away, you and your flashlight would just fade to black.
I mean, this just goes to show you, our intuition, the stuff that works for us here on Earth, it completely breaks down when you get to the extremes of the universe. It really makes you wonder, doesn't it? What else about the cosmos do we think we have all figured out, but is actually far, far stranger than we can possibly imagine?